And without further ado, we have Gleep presenting Reverse Engineering 101. Anybody who knows me knows that I love this topic. And maybe some of the things you learn will help you in the CTF and deobfuscation contest. So take it away.
Morning, everyone. My name's Gleep. We're going to get started here. I do need to pour myself a little. So for those of you who don't know me, my name's Gleep. I'm a member of Null Space Labs. We're going to go up into Reverse Engineering 101. Just a quick show of hands. How many people here have never, I assume a lot of you are programmers. How many of you have gone the other way, taking programs apart? I know you. Okay, well good. This is a good group to start with. Reverse engineering is a really interesting topic. I've been interested in it for a long time. I'm still learning it. So we're going to go in and start here. I'm going to take off my hat here. Everyone knows me by my hat. I pretty much never take it off, especially when I'm at con. But it does kind of get in the way sometimes. So this is what my hair looks like. I know, isn't it right? Pretty. So who is this dude? My name's Gleep, as I said. I'm a network engineer and a network architect, formerly with Nortel Networks. Now I do Cisco, Avaya, HP, and Juniper. I am not a professional reverse engineer. I don't do this for a living. As I said, I'm a network engineer. I'm a network guy, network security, and that sort of stuff. It's just an interest of mine. I'm a malware analyst, amateur, and a capture the flag player. I do teach occasional assembly language classes at Null Space. That's kind of an exaggeration. I think I've done maybe 2 or 3, and they tend to space kind of far apart just because of real life issues. That's my contact information, gleepdc at gmail.com, or you can get me. I do run DEF CON 805. DEF CON 805 mainly consists of me sitting in a bar drinking with lots of blinky stuff around me. So if you ever are actually up in the Ventura County area, I do put out notices when I'm going to be at the bar with my drinky stuff, with my blinky stuff, doing drinky things with blinky things. And so come on by and sit down and we'll talk about hackery things. So this talk is more about process than tools. The tools can vary. It depends on personal preference. But the process, the mindset is a lot more important than what tools you're actually using. Prepare for a lot of self-directed study. This stuff is not easy to learn, and it can be very esoteric. So you kind of have to push yourself and do a lot of exercises. As I said, I'm still learning. I'm not a professional at it by any stretch of the imagination. It can be very, well, that's out of order. It can be very frustrating, but keep trying. Remember, in the arms race between malware writers and reverse engineers, the reverse engineers will always win because the stuff still has to run on the computer. And if it can run, then we can decode it, we can debug it, we can figure out what's going on with it. Do exercises, write stupid little programs and then disassemble them and see how they showed up. See what your compiler did to that program. It doesn't have to be anything really big. It can just be a couple for loops, maybe a case switch or something like that, and see how it shows up in assembly code, and you'll get familiar with how that assembly is going to show up, is going to represent your higher level language structures. Crack me's, keygen me's, you can get malware examples. There are several good malware compilation websites out there that you can join and get live malware samples from and take them apart, see what they do. I do have a resource page listed at the end if you guys want to take a look into some more things for that. So as I said, this talk is to kind of help you guys introduce you to one process, my process for reverse engineering. It doesn't have to be yours. People like to do things in different orders. Some people like to do dynamic analysis first because it's quick and they get a lot of quick indicators of what the malware is trying to do. And then they go in and they reverse statically a lot of the interesting features. So why would you want to reverse engineer in the first place? You've got a perfectly good program. Why not just leave it the way it is? Well, you can do a couple of things with it. You may be interested in how it's doing a specific feature. You may say, oh, that's a really cool thing, but you don't have the source code. So you want to go in and see how it's actually accomplishing that feature. You might want to find hidden information, especially if you're in a capture the flag situation. Capture the flag writers love reverse engineering challenges. You have to take them apart and either find the flag that's been obfuscated in the code, or they have to reverse if the flag is programmatically generated. You have to reverse the algorithm that's creating the flag. To get around protection schemes, you might be surprised, or you might not, to see just how laughably bad a lot of copy protection actually is. You could have there was one I was reversing. It was a program that had a big long license string in order to see if you were a valid user or not to enable certain features. And it had a big DLL that's only job was to take that license key and figure out what features you were entitled to. And it went through all these machinations and folding, spindling, and mutilating that flag in order that key in order to come up with what features you were. But at the end of the day, it would come back and say, are you valid? Send a 1 back. If you're not valid, send a 0 back. So as a reverse engineer, what do? You just make it a 1 all the time. It happens a lot. You'll be very surprised. To make money, there are people that make their living off of finding bugs. There are bug bounty programs for existing commercial packages, and some people make money off of it. Now, do they make a lot of money? It depends on the bug they find. If they find a lot of small, kind of not so high dollar value bugs, then they'll get less money. If it's a very big, wide impacting bug, then there are places like Zero Day Initiative that will actually broker the bug bounty programs. Other companies have direct bug bounty programs that you can submit bugs to and make money that way. You can also sell your 0 days to other people, such as, the bad guys. They tend to pay really well, but then again, you like your kneecaps, don't you? To add or disable features or functions. You may have a program that you may say, this is a cool program, but I want to add on to it. And you may need to figure out how to inject your own specific feature or code into that program. To develop software signatures and indicators of compromise. This is what the malware or the virus companies do. They gather all the hundreds of megabytes or gigabytes of viruses and malware from around the world every single day, and they sit there and they take them apart and they see what the malware is trying to do, and they develop a list of what it's trying to do when they write a signature that then matches that particular strain of malware. And so if you're working at a company that you need to find out if a specific piece of malware is present on your work's computers, you can develop indicators of compromise that then you can go and do a search for that on other computers in your system without having to go through a full huge scan. You can develop a targeted indicators of compromise. For shits and or giggles, yeah, sometimes it's just fun to break things. For some people, it's just a puzzle. I'm one of those people. It kind of interests me. It's just a personal preference. Step 1, learn assembly language. Sorry. Sorry. There's really no two ways about it. When you're reversing a program, when you disassemble it, you don't get source code out of it. You get assembly language, and you have to know what you're looking at. That said, you do not have to learn all of assembly language. Okay, there are hundreds, if not thousands, of operation codes depending on what architecture you're working in, but you don't need to know all of them. There are a subset of those opcodes that are used all the time. Jumps, moves, copies, string compares, that sort of stuff. And then there's weird ones like MMX or the SSE stuff or 3D Now that aren't really used a whole lot. You don't have to go and memorize them. If you get one of those functions in your disassembly, you can go and look it up. But the main opcodes that everyone uses are well known, and you'll get to recognize them very quickly. So the reverse engineering environment, virtual machines are your friend. They make it very easy to analyze something and then reset back to a known good state without having to reformat your hard drive. There are people that have a reversing setup that consists of a standalone machine that they image and then it runs, because sometimes malware and other programs can be virtual machine aware, and they change their behavior based on whether or not they detect a virtual machine. So that's one benefit of having a standalone system that just does malware analysis or whatever it is. So you build out your VM with all your tools and instrumentation, then you snapshot it. That's not news to anyone. You do have to isolate the VM from the network because you don't want to be infecting the rest of your organization. But you have to remember that your host that is hosting the VM is also a node on that isolated network. So you have to make sure that your current computer, that the host computer is patched, and so you don't get the clap. And then, as a good neighbor, isolate your host machine from the network if it's something that's particularly nasty, like a worm or something like that. The tools, everyone starts out with a disassembler and a debugger. The disassembler, the gold standard, is IDA Pro. There is a free version available, and it's awesome. The IDA Pro paid version is even more awesome, but it's also money. Lots of money, especially if you get the Hexrays decompiler. IDA Pro Professional, the full paid version with Hexrays decompiler is almost $5,000. So for amateurs like me, it's not cost effective. If anyone all want to pay me to get it, I'll get it happily. Specialized disassemblers for some languages do exist. Like if you're working with .NET, they may present the information a little better. If you're working with Flash, you can use SWF Investigator from Adobe. If you're working .NET, .NET Reflector, Grey Wolf, they can take apart that bytecode and that program and present it in a little better way. Debugger, your usual choices are Ollie Debug or Immunity. Ollie Debug has been around for a long time. It's still supported. It's a great program. There's a lot of plugins and scripts available for Ollie. Immunity, if you don't know, Immunity, basically they took Ollie Debug and rewrote it with a Python backend, so that allows you to write Python scripts. Immunity is kind of geared more towards vulnerability analysis, and Ollie is geared more towards reverse engineering, if that makes sense. GDB for Linux for the OGs, if Datagram's back there, yeah. Woo, GDB. Yeah, it's Datagram. It's actually on the Nullspace Labs website. He has a GDB init program for GDB that really takes it to the next level. WinDebug or WinBag for Windows kernel debugging. It's kind of the only game in town. For those of you who are familiar with Ring 3 versus Ring 0 debugging, for Ring 0 debugging, getting into the Windows kernel that's not just user space debugging, kind of WinDebug is the only game in town that really gets access to those system levels. Other tools that you'll run into, PEID, it's still around. The guy that developed it is no longer updating it, but there is a version available. It's good for kind of general PE investigation. It'll show you the PE headers. It will show you the sections, OEP, things that we'll get into. It can also identify a lot of common packers. And for certain packers, it actually can unpack the program for you. Lord PE is another program that's available. It's useful for, its main kind of claim to fame is once you dump an unpacked program out of process memory. It may or may not have its import address table fixed, which is necessary for it to run separate without the packer. And Lord PE can help reconstruct the PE header and the IAT. Other plugins that you might find useful, OllyDump or OllyDump X. OllyDump X is the new version, and it is available for Olly, Immunity, and I believe it also has a WinDebug version available as well. OllyDump is useful for, again, once you unpack a program, you can then dump its memory space into a file, and then that file the packer has been stripped off, and you can get clean code out of it. It can also be useful for finding the original entry point. We're going to talk about what those are in a little bit. It has some specific trace features that allow you to go into the assembly and kind of step through the section hops to find where the packer ends and where the real program begins. What's up, man? Mona.py from the Corland team is amazing. If you're into vulnerability analysis, use it with Immunity Debugger, and you can do things like find ROP chains for you. It can find all instances of jump BAX in your code and give you a list of where they are in memory. It can do a lot of really very cool things. TLS Catch is a little plugin for Olly. It's useful for trapping thread local storage callbacks, and we'll get into that in a little bit. A hex editor to edit the hexen. Yes, sometimes you just need to edit a program. Sometimes you need to change a header or something like that, and hex editor is useful for that. So sort of some of the lingo, you'll hear original entry point all the time if you're doing reverse engineering. Every program in DLL has an original entry point where the program is going to be loaded into memory. And there are several common places that they are usually loaded into memory. Hex 400,000 is one of them. And because memory is virtualized, all of these DLLs and all these programs are going to try and load into the same memory space. Windows says that's fine, and it just maps them between virtual memory and gives them their own virtual memory page, and then maps it over to a real memory location. And that's all behind the scenes. So all of these programs all think they're at the same memory location, but they're actually not. They're just virtually mapped. The original entry point forms the base address from which relative virtual addresses are calculated. So when programs are built, the programmer doesn't know where the various functions are going to reside in memory, especially with newer operating systems where they're using address space layout randomization. They can be all over the place. And so they may say, well, I don't know where I am, but hex 1,000 bytes that way is a function that I need. So that's a relative virtual address. From wherever you are to wherever you need to go, the difference between those two is the RVA. So this is what we just talked about. So it's a memory offset from the base memory location of an image. So your DLL is loaded into memory, and then you say, well, for this message box A function, it is 1,200 bytes down from my original entry point. So yeah, say you have a image that got loaded into hex 400,000. If your relative virtual address is hex 1,000, then your virtual address for that function or that piece of data would be at 401,000. Does that make sense? So the import address table is really important. It's a map of all the various functions that a program needs to run, and the memory location where those the memory locations of where those functions are. When you're programming, again, you don't know where these DLLs are going to load into memory. So we call them by their function name, and then the Windows loader, when it's loading up the PE file, then maps the function name to where that function has been mapped in memory. This is important for working with address space layout randomization. Before we had ASLR, virus writers and other people could count on functions being loaded into specific memory locations so they could statically code those. ASLR was put in to help combat that. So a DLL that you rely on to make your virus run may no longer be at the same location all the time. It can change. Windows can randomize where it's putting it in memory. So unless all your needed functions have been statically compiled into the program, you're going to have imports. A program will have an import table of, say, I need message box A, I need get process address, I need get module name. I need all these functions in order to work with the Windows system. Unless you statically compile it, you can do what's called static compilation, where you when you're compiling your program, you say, I want all of the functions that I need to be wrapped up into my program, and it doesn't need to call anybody else. The problem is it makes your program huge. And so in order to keep things small, you generally will have Windows API calls, which means you have to have imports. So the general process for reverse engineering is identify what kind of file it is. Then you identify whether or not the file is packed. And we're going to go into packers in a little bit. You might want to look for interstring strings. Don't take the strings as gospel. They're guidelines. They're not going to be end-all, be-all indicators of what the program is. Check its imports and exports. You can tell a lot about a program by what imports, what functions it's going to be calling. You might possibly want to upload to VirusTotal or Malware. There are two websites. They have a large list. I think VirusTotal has like 48 different antivirus engines that it will submit your program or file to all 48 of those virus engines all at the same time, and it'll get back a list of what each of those virus engines detect that file as having, if anything. You can also upload MD5 MD5 string or hash of your file and search on it to see if that file has already been reported. Why you might not want to do this is if you are working at a company and you think you have a piece of malware that is targeted to your company. Say someone wrote a virus just to get into the bank that you work at. Well, if you upload it to VirusTotal or Malware, you've just put up a big red flag to the person that wrote that malware saying, oh, your program that you wrote for this company is being reversed. They're on to you. And then all they have to do is change a couple things, repack it. It's got a different MD5 sum now, and send it out again. And you've got a new variant. So you may tip your hand because the virus writers watch these websites, and they'll submit their own MD5 hashes to see who's checking it out. If the executable is packed, then you would dump it. You would try to unpack and then dump it out of memory into a separate file that strips the packer off. And then you'd go into, I like to do dynamic analysis first, just because it's quicker. You get a lot of information out of what the malware is trying to do, and we're going to go into how to do that. I do actually have a little demo if we have time. What I don't have a demo of is static analysis, because there is nothing more boring than watching someone else paw through code. So we'll talk about it, but I'm not actually going to do a demo. So identifying the file type. The file has to run, so even if it's masquerading as a file type, they'll still leave some clues as to what kind of file it is. Every file starts with a magic number to tell the operating system what kind of file it is. For PE files, for Windows files, it's MZ is the magic number. If you look in a hex editor at any file, any executable, you'll see an MZ at the start. That tells it that it's an executable. That tells Windows that it's an executable program. Same thing for Linux. Its magic number is .elf. And some malware might pretend to be a different kind of file, like a PDF. It'll have a PDF extension, but if you actually look at it, it's an executable. And some malware might actually have invalid PE headers. You can mess with the PE header and change some of the files, like the file size, in order to mess with debuggers. Debuggers can be much pickier than Windows, the operating system, actually is. Windows will still try to load it, but the debugger will say, it's an invalid PE header, and crap out. So they're doing that to make it so it still runs when someone tries to run it, but it makes it that much harder for the reverse engineer. If you reverse for any amount of time, you're going to run into anti-reversing techniques, and there's a lot of them. There's a really good paper written by a guy named Peter Ferry. I'll give you a link at the end, and that has a huge list of the anti-reversing techniques that are out there. So the first thing you're going to run into is packers. A lot of malware is packed, and we're going to talk about those next. The malware might check for a debugger or for a virtual machine. They might do something called a thread local storage callback, and we're going to talk about those in a little bit. Basically, with thread local storage, it's abusing TLS in order to make sure that code runs before you actually hit the first breakpoint in your debugging session. Same thing, structured exception handling shenanigans. With structured exception handling, normally structured exception handlers only operate when there's an error in the program and they have to catch an error. But malware and virus writers and capture the flag writers like SEH in order to hide their code, and we're going to go into that. They might try to encrypt stuff or encode their URLs in some way. One area that I find really interesting and we're going to talk about is embedding junk data in the code sections. You wouldn't expect code to be expect data to be there, but if you embed junk data, you can actually garble the disassembly. So the first thing is to see if it's packed. So packers are used to shrink files, but they can also be used to obfuscate code and make it harder to analyze. Some packers are better at this than others. Some actually will insert their own SEH shenanigans and other things like that when they're packing the file. PEID can identify many common packers. UPX is still the most common packer. UPX is a free packer that you can get. Just do a search for it on the internet. It's out there. It's not sneaky in any way. It just packs the file. One thing that you'll notice about packed files when you're debugging, when you're disassembling them, is they'll have very few imports and exports. And that's because when the packer runs, it mangles things. And they only want enough imports just to do the unpacking, and if they build in any anti-reversing features. So as I said, the packers shrink the file, but while they're shrinking it, it also destroys the import address table that the original program had, and it scrambles the file. And then once the file is packed, the unpacker stub program gets added onto the front of the file. So the stub's job is to unpack the file, rebuild the import address table, and then once it's done its job, it gets out of the way and returns execution back to the original executable. If there are any anti-reversing features to the packer, the stub is also going to take care of doing those features. Some packers are really complicated. Themida is one of them. It actually has a kernel component as well. But no matter how complicated it seems, they can't make it so complex that it doesn't run and it's not reliable. So there's always a way to unpack or reverse. Ways to unpack files, you can run it. It'll do its job. It'll unpack. It'll run just fine, but you will get infected with whatever it has. You can then dump from process memory, but you're still infected. You can use an unpacking routine, a plugin. There's actually some websites that will unpack your program for you and mail it back to you. Or you can use a program. So like if you get UPX, and if you know UPX was used to pack the program, just use UPX to unpack it. That's fine. The ones that you're not going to have unpacking stuff for are custom ruled packers. Some guy wrote his own packer. You're not going to have, unless he's used that packer a lot, someone's already written a script or something for it, or a plugin. You can unpack manually. Ollie script is a plugin for Ollie debug that adds on a scripting language, and it has some features that allow you to actually write a script that will unpack for you. And then if you go on openrce.org or some of the other websites, the reversing websites, you'll actually see a huge list of scripts people have written to unpack various packers. You can use Ollie debug or Ollie dumps trace by section hop to find the tail jump. We're going to go into what the tail jump is in a second. You can open in the debugger and find the tail jump, and we're going to go into that in a little bit. Because a lot of packers store the original entry point in EAX after unpacking, so you would look for a jump EAX. That's one way to do it. If you're, I don't think I put this in a bullet point, but if they are doing structured exception handling shenanigans where they take the structured exception handler and then they jump to it, they force an error and jump to structured exception handling, then what you can do is on the first entry of the structured exception handler in memory, you can actually set a breakpoint on access. And then when that, because a lot of packers will clean up the structured exception handling chain before they return execution back to OEP. So if you set a breakpoint on access for the structured exception handler, when they clean it up, after it's done unpacking, then your breakpoint will hit and you'll be right before the tail jump. A lot of tail jumps may have a long jump followed by a bunch of null data. You'll see, because the program reserves memory space, right? But it's packed, so not all that memory space is filled. So you have a jump that's going to take it back to the original entry point, but then the data space that the program takes up hasn't been filled out yet. It hasn't been populated by the packer. The tail jump is where the unpacker function has done its job and then it returns the control of the newly unpacked executable back to it. So you set a breakpoint on the tail jump, you run to the breakpoint, and then once you're back at the original entry point, then you would dump the program out of memory. I do have a little demo. It's really nothing awesome. We're gonna pack something and then see how it shows up. Oh yeah, oh yeah. Sadly, my mouse sucks on the surface here, so we'll see what we do here. Ooh. So we got the venerable calc, and we have UPX here. So calc's a benign executable, of course. So if you want to pack it, we would just say cc.exe calc.exe. Okay, so we've packed our file. This guy over here is packed. That's the original calc. You can see this guy is 112K, and this guy over here is 55K. Oh, yes. So if we, this is a really bad resolution. Okay, so we've got, where do we got here? We got, oh, there we go. So here's PEID. So take a look at our entry point here. It's 12475. You're going to want to remember that. Our sections, over here we have a text, a data, a resource section. And then there are imports and exports are over here in our import table. So you can see these are all of the Windows APIs and Window API DLLs that we're importing. These are all the functions. Down here are all the functions that we're going to be using in the program, right? It's a Windows program, so it's got Windows, and all the Windows stuff is in user32.dll. Fine, great. Okay, so if we do the same thing with our packed executable over here, you can see that right there. You can see that our sections have been renamed, UPX0 and UPX1. You can see that our entry point has changed. And you can see right here that PEID has helpfully told us that it's packed. If you look over in our imports and exports, we have no exports right here. Our imports, all the functions that we were going to see in our original program are gone. They're packed. So the import address table has been chewed up, and a new one that the packer needs has been substituted in its place. So, as I said, you can unpack this with the program that it was packed with. You could unpack it with UPX, of course, but we're not going to do that. We're going to do it the hard way. So we're going to go into Ollie debug. We're going to open this guy. And one thing that you'll notice is when I come in here, I'm going to run to my, when you see this thing, when you're analyzing something in Ollie debug, just say no when it asks if you want to continue analysis. The analysis that's going to give you, because the program is packed, it's going to be wrong. It's just going to confuse you. Just ignore Ollie and say no. So here we are. We're in module CC, which is our main program. And here's our original entry point. You remember that 20C50 was our entry point for that packed executable. One thing that I like to do when I come into the main program is I like to kind of look around. Look down here at the bottom. You see all these zeros? That's all that empty memory space I was talking about. That's all memory space that's going to be filled up when the program is unpacked. It's allocated, but it's not initialized. So one thing that I like to do is I like to go back up to the top of where that null data is and look and see what's there. Oh, look. Remember that 12475? That's the original entry point. That's the tail jump. So we're going to set a breakpoint on that, and we're going to run to our breakpoint. So we've just hit our breakpoint. We're going to F7 to jump, and here we are, 12475. That's our original entry point, and then you would say plugins, Ollie debug, dump debugged process. And for this, you can accept the defaults. And you just say dump. And it'll say, what do you want to call it? And we're going to say cc dump.exe. So we've got this new program over here. It's now a stripped version of our packed program. You can see our original entry point's been fixed. One thing over here that's kind of interesting is it's still got UPX0 and UPX1. It didn't bother to go and fix the section names. But if you look over here in our import table, it did go ahead and rebuild all of the functions that we need to run the program. So the question is, does it run? Let's find out. Yeah, it does. So that's the basics of unpacking. UPX is not trying to be sneaky at all. It just shrinks the file. There are a lot trickier packers out there. So that's that. Let's go back to our thing. Where it is there. Okay. Yeah. Okay, yes, and. Okay. So another thing that the malware might try to do is check to see if it's being run in a debugger. And there's a lot of ways to do that. Hold on. Scotch. Oh, that's so much better. Okay. So the most common way that's going to check for a debugger is a little function called isDebuggerPresent. It's actually a wrapper for about 4 lines of code. You might see it either way. It might do a call just to isDebuggerPresent, or they might actually just say the 4 lines of code. It actually checks for some flags in the process execution or process environment block. There's also one called check remote debugger present. If you start seeing these system calls or these API calls show up, then it's looking for a debugger. NT-query information process. All of these are looking for various flags or conditions being set on the program, because the debugger, when you load up that program into a debugger, it sets things so that it can interrupt the process flow in order to be debugged. The process environment block flags, there's one called being debugged, and there you can also, there's a flag that gets set for the heap status that can be checked by the malware as well. Timing detection is an interesting one. Basically, if you see a system time check, and then it runs some code, and then it does a system time check again, and does a compare. Normally, in runtime, there's not going to be a whole lot of time between those two checks. But when you're debugging and you're single-stepping, there can be a lot of time between those two checks. And so if you're seeing those two compares, those two time checks, then a compare, and then it craps out on you, it's probably doing a timing check. It might do a search on open windows on your system. Say, is there an Ollie window open? Well, then it's probably being debugged. It can check the NT-global flag, where there are some flags that it's a flag in the process execution process environment block. It can do a checksum on the memory. The virus writer knows what it was when he built the thing. But when you attach a debugger to stuff and you start inserting breakpoints, it changes the checksum of the file. It changes the checksum of the memory. So they can actually generate a checksum on the memory and say, well, if it was different from the way I built it, then it's being debugged. The virus or the malware might check for a virtual machine. VMware is not stealthy. VMware tools, do you have a question? Or? Oh, okay. So, VMware tools has a lot of registry keys. It has system drivers. It has a lot of stuff that makes no effort to hide. And so you might see your malware actually go and look for those things to see if it's being run on a virtual machine. There's a bunch of instructions that VMware might use, but they're not common instructions to be found in a regular program. So if you start seeing system calls or system checks to see if the memory locations for certain system calls are different than known values, then it would deduce from there that it was being run in a VM. So thread local storage callbacks, one thing that you'll see. Thread local storage is used to, in the real world, in the nice guy world, to initialize data in threads for a process before the process starts. Now, if the malware has code in thread local storage code runs before the main program. So if you set a there's an automatic breakpoint that's set when you start up a program in Ollie debug, or an Ollie debug, and if the code has TLS in it, that code will run before you hit your breakpoint. So some things that it can do, there's no limit to what you can put in thread local storage. It can be any code you want. So some things that you can do is have it remove breakpoints. So the debugger is trying to add breakpoints, and the TLS code then takes those breakpoints out, so you get infected anyway. So malware writers often use TLS to check for debuggers or virtual machines. You can put function calls in there. And then either crap the program out and start deleting stuff, or switch behavior to something more benign, or act like something different. It's also kind of easy to spot, though, because it does add a section into the PE header. It adds a .tls section into the header. So if you see this, you'll want to change how the program is being, how you're putting your breakpoints in. That's why I use TLS catch is one of the plugins that I like to use, because it sets breakpoints on TLS automatically. Structured exception handling shenanigans. How are we doing on time, by the way? Time's up. Oh, you're all right. Excellent. So structured exception handling. Again, in the nice guy world, structured exception handling should only be called when there's a bad error on the program. You want to catch that error and do something constructive with it instead of just crash, right? So structured exception handling is a linked list of code segments that should only be executed in case there's an actual big error in the program, but it can be abused. Malware writers and all you capture the flag writers out there abuse this by putting their own code in structured exception handling chain, and then they force an error. They make something bad happen in order to divert program flow away from the normal program flow in the program, and then they send it over to SEH because that's it just if you're setting a breakpoint in a certain area, but the SEH chain happens, that error happens before your breakpoint, you never hit your breakpoint. It just goes to the SEH chain and executes anyway. The first pointer to the structured exception handling chain is stored at FS0. Again, as you learn assembly language, a lot of these meanings will become more clear. And then the rest of the SEH chain is stored on the stack. So what you'll see if you have a malware that is doing a structured exception handling chain is you'll see them insert their own code into their own memory addresses into a structured exception handling chain. And then once they hook themselves into the SEH chain, then they'll do like divide by 0, which causes the error to jump over to SEH. So SEH, basically it consists of a link to the next element in the SEH chain and then the error handler itself. So as an error happens, the system just goes from error handler to error handler to error handler until it finds one that can handle the error that occurred. This is what I was saying earlier, you can find, if you have someone that if you have a piece of software that is doing these kind of structured exception handling tricks, if you set a breakpoint on your memory that forms the first entry to the structured exception handling chain, if it's unpacking, the malware will usually try to clean up the SEH chain before it transitions back to the original program. So if you set a breakpoint on that memory access, on access for that memory location, you'll see it when it'll hit that breakpoint when it passes back through and undoes its SEH chain. So that's one way that you can find the original entry point. People might encrypt stuff and encode stuff. The thing with encryption, it can be a real pain in the ass. But the thing that you have to remember is it still has to be decrypted before it can be run. So if you have someone that's encrypting everything, you might not get a whole lot out of static analysis. You may have to actually do some dynamic analysis and dump it out of memory after it's been decrypted. One thing that you'll run into is people like to base64 encode stuff, but everyone knows base64. The way to make it a little bit tougher is to have your own base64 alphabet. You change it up so that, because otherwise, if everyone just uses the same base64 alphabet, you know, you can just go online and go to a base64 decoder and decode all the way. Another thing you might run into, it's kind of goofy, but people still do it. You might run into octal or hex or dword URL encoding. For those of you who aren't familiar with like dword encoding, basically everything on that URL before the @ sign is completely meaningless. The actual IP address for that service is actually in the number on the end. You got who's familiar with dword encoding? Yeah. Okay. So basically, you take an IP address, right? And you multiply the first octet by 256, and then you add the second octet. And then you multiply the result of that by 256, and then you add the third octet. Then you multiply that by 256 and add the fourth octet, and you have a dword. Basically, it's creating a binary string that if you look at it in total, it adds up to that, but you reverse it out. If you look at that dword in like a scientific calculator, you can see the binary version of that IP address in each of its octets. So there are some great websites out there for DWORD and hex and octal encoding. Yeah. Oh, okay, that didn't end up right. They can embed junk data to change the offset for disassemblers. So if you look at what's happening here, you see this this XOR EAX that makes EAX 0. Then you see jump if 0, a near pointer 1 byte over. So it's jumping over this junk opcode right here down to this instruction right here, and then it returns. That's what it wants to do in runtime. But if you put it into a disassembler, the disassembler is trying to make things, the disassembler is trying to make things nice and pretty for you. So it's trying to interpret all of these commands, including the junk ones. So what the disassembler would come up with was, oh, here's our EAX, and here's our jump, but then it gloms all of these things together and gives you a jump to some weird non-existent memory address. It's just tricks to fool the disassembler. Oh, that's nice. Okay. So you might see jumps to the same target, where a jump if 0 and jump if not 0 going to the same place. These are all just tricks to mess with disassemblers. You might see, this is a really interesting trick, you might see jumping back into the middle of a previous opcode. It's weird. Look at this. So here's what the disassembler thinks happens, where it's moving this instruction into AX, and then it XORs the AX, and then it jumps back 7 bytes into the middle of this guy right here, and then the disassembler then reads this as what happened. What's actually happening at runtime is this jump happens, and then it jumps back to EB05, and it realigns all the opcodes. So what actually happens is it jumps forward 5 bytes, which, 1, 2, 3, 4, 5, to 58. 58 by itself is pop EAX, C3 is return, and then 2 nops. So that's what's actually happening. But by inserting this weird little backwards jump, it completely realigns everything that happens after that. Now, for those of you who have done reverse engineering, has anyone seen a compiler that actually does this? You think Visual Studio does this by default? No, I haven't seen anything. Have you seen a decompiler that does this, or a compiler that does this? If not, you may be looking at my next talk. I want to build something that does these kind of jumps, that does substitutions like this, because it's pretty awesome. So if you're going to analyze something dynamically, the process, take a snapshot of your VM. I don't care what else you're doing. Take a snapshot first, just so you don't have to recreate your VM. Start your monitoring tools, and then run the malware. See what it does. Watch for its behaviors. And then kill the malware process, stop your tools, gather the data, interpret, reboot, and do it again. So things that you might find useful for evaluating malware, or anything else for that matter. Process Monitor, it's by the System Internals guys. They used to be a separate company, then Microsoft bought them. Process Explorer, Redshot, this is the URL for it. Obviously I need more scotch. Redshot's a great program. It's a source storage page for it. It allows you to take a snapshot of everything that's going on in your system, all of the registry entries as they are, and then after you run your malware, you take a second snapshot. It tells you everything that changed on the system, all of the registry entries, all of the files that were created, all the files that were deleted. Another one, Capture.bat. It's off of HoneyNet. It is a great little program. You can run it with options that Anything that gets deleted on the system during the malware while you're running it gets automatically copied and saved into a directory. It will also capture network traffic as a PCAP file. So anything that happens during that event, it will capture and save off. So it's a handy little program to have. Wireshark network sniffer, everyone knows it. FakeNet. FakeNet is a program that was made by Sikorsky and Honig, the guys who wrote Practical Malware Analysis. It is pretty awesome. You'll see it run. Basically, anything the malware asks for, FakeNet will provide. It wants a DNS entry for some IRC server over in Romania? Sure, it sends it right back. It's sending itself, but it's sending it right back, and it saves all of the traffic that it sends. You can send, if it's trying to mail something, it masquerades as a SMTP server. It'll masquerade as a web server. It'll masquerade as SSL secured web server and decrypt the traffic. It's cool. I do have a little demo here. So, how am I doing on time? Awesome. This mouse sucks balls. Yeah, boy. Yeah, boy. All right. Let's get rid of that. And we don't need Ollie anymore. So what do we need? We need capture.bat, and we need. So we're going to run a little piece of malware here and see what it does. CD program files /. So I'm going to start up FakeNet. So yeah, like I said, it'll masquerade as basically anything you want. And then I'm going to start up Redshot and take a registry snapshot here. Start a process hacker. Ooh. Let's minimize that guy, because damn. And where'd my Procmon? Redshot. Take a first shot. Scotch break. Speak to me. Almost done. Almost done. Almost done. Are you done? No. Are you done? No. Almost there. Okay. So while that's going on, come on. Come on. Always hard doing stuff in virtual machines. So what we're going to do is start up our monitoring tools, and then we're going to run this little piece of malware and see what it does. Okay. So now that that's done, we are going to start up capture.bat. So for capture bat.exe, and we're going to say save copied files and network traffic. And it's actually got, all right, fine, there. So it's actually got a system driver for CaptureBat, and that allows it to copy stuff at really low level. It's kind of awesome. So now we've got our malware over here, and we're going to see what it does. Oh, it deleted itself. Remove me 4785.bat. Okay, well, that's something interesting. Service SVKP has been created. Okay. Did anything happen over here in FakeNet? No. Nothing. Okay, so nothing really happened. Awesome. So what was it looking for? Let's take our second shot. Maybe go over here in our CaptureBat and see if it was looking for anything in particular. Outputs, services, LSAS. Awesome, not responding. That's what I love. So let's filter on maybe. Of course, everything's running like shit. Yeah, the demo god's not kind today. So, I actually know what's going on with this. This particular piece of malware does VMware, is VMware aware. Oh, it did come back. Okay. So here we're going to do our compare on Redshot. This particular piece of malware is VMware aware, and it changes its behavior. If you come down here, you see it's creating a service, that SVKP file. And it deleted malware.exe. It did add another, it added this svkp.sys file here. And it created a little batch file called removeme4785.bat. So if we stop capture.bat and we look here, then it's got, if you go into the logs directory, and it's got deleted files. It's got cc, doc settings, administrator. So there's that remove me 4785. If we see what it's doing here, it's deleting the malware.exe file and it just goes back to itself, just to double check that it's been changed. Okay, so nothing much happened there. What we're going to do is we're going to restart with a new snapshot. And we're going to do it again, but we're going to take out VMware. And it will change its behavior. Hooray, snapshots. Okay, so second verse, same as the first. We're going to start up our, first thing we're going to do is we're going to remove VMware. So, I hate this resolution. It's terrible. What am I doing here? We're going to do HQ local machine software VMware. And we're just going to delete all of those guys. It's a snapshot, right? Who cares? So now we're going to see if this thing changes its behavior at all. Okay, and then we need our Procmon, process hacker, redshot. How am I doing on time? Oh, good. It's lunch, right? So we're going to run this malware and see what it does now. Is my VM going to run any better now? Hope so. Hopefully this thing cleared out a little bit of memory.
So that machine is still on VM, right? But you just delete the registry VM so that the malware will detect the registry.
Correct. It didn't show up really well. It's kind. The question was. Sorry.
You're still on the VM, but you just delete the registry.
Right. This particular malware, when I was writing the demo for it, it detects VMware by looking for registry keys. So I went and I deleted the registry keys. It takes a while to sort through, which is why I didn't show you the whole process, because it's kind of a pain in the ass, but it does actually look for registry keys. So I just deleted all of the VMware registry. This thing's still going, damn. All right. You're going to see when we run this that it changes its behavior, provided that the demo gods are kind. All right. Let's do this thing. Fake net's running. Let's run our capture bat.exe-c. Right. Everybody ready? Let's see what happens. So we're going to go over here and we're going to open that guy right there, and we're going to run our malware. Oh, look. So another thing that FakeNet does, which is kind of cool, is if a malware asks for a program to download and run, it'll actually give it a little mini program to run that just pops this little pop-up. Says, I downloaded a program and I ran it. It's awesome. So I highly recommend FakeNet. It's really a little cool program. And again, if it's SSL encrypted, it includes an SSL certificate, and it'll decrypt the traffic for you and give you the raw text, which is awesome. So usually if you were using Wireshark, you just get the encrypted traffic, which isn't a whole lot of use to you, right? So yay, FakeNet mini program has been run. So if you look here, where are we going? Where are we trying to go to? hp-witlog.com, and then it says get tds.exe, and so FakeNet happily responds with its own tds.exe, and that's just me trying to get a Windows update. And then and it looks like its command and control might be over IRC, might be a bad IRC channel. So that's the demo, guys. There's really not a whole lot left to this. we're going to exit out of this here. I love you too. I love you guys too. I'm gonna miss you guys when I'm leaving for Japan in August, so I'm gonna miss you guys. I know it sucks, but you know it's Japan, so what do you do? That's totally how that works. Okay, so back to this. There's like 2 slides left, so you know, who cares? Oi, Gewalt. All right, come on, shut up. Thank you. Wonderful. Yeah, let's minimize that. And go back to this guy. Yeah. Static analysis. Watching me plow through code is boring. IDA pros with Hexrays decompiler equals win equals $5,000. Oh God. If any of you guys want to pay me to buy it, I will happily buy it. It is win mode. It's all it. Just to be clear, Hexrays decompiler does not give you source code. It gives you Hexrays approximation of what your source code might be. It gives you pseudocode. So if you want to, it's great for coalescing hundreds of lines of assembly code down to like 5 lines of pseudocode. So if you just want to see what a function does, it's great, but it's also buku bucks. The first step for static analysis is to unpack what you're looking at, and so you get clean code. And then the first step is to look for strings, imports with your clean code, and then go into, you're not going to find anything interesting in the Windows API. You don't need to reverse those functions. But you would look at the original executable. If it has any specific DLLs that come with that executable, you'd want to look into those and go from there. So for some resources, there are some great resources out there. There's actually a ton. Books I used in developing this is Reversing by Eldad Elam, Practical Malware Analysis by Sikorsky and Honig. I cannot recommend enough. This book is notable in that not only does it include a full kind of program on malware analysis, but it also includes exercises and example code and things like that that you can actually use to train yourself to do malware analysis, and that's really invaluable. The IDA Pro book by Chris Eagle is great. He's an amazing programmer. Corlan, the Corlan team, if you're not familiar with them, are Uber. Toots for You is a great website. It includes a lot of tutorials and things like that. You can find whole reversing courses on there. Crackmes.de is a great website for finding little totally legal reverse engineering programs. OpenSecurityTraining.info has a lot of great resources for learning reverse engineering. Dino, what the hell is his last name? Vidovi or something like that. He's a great guy. He works over in New York. OpenRCE.org, and then that anti-debug paper that I was telling you about is Peter Ferry, and it has an enormous list. It's 150 pages long, full of anti-debugging and anti-reversing features. And then Trail of Bits, the company, just released a great ebook. It's all on CTFs and CTF playing, but it has a very large reversing component to it. So I would encourage you to go and look at that. That's the talk, guys. Thank you. If you have any questions, I'll be around all con long. Look for the hat, because I'll be wearing it the rest of the time. Thank you. You got to get one with the hat on, because that's how everyone knows me. There you go.
Sure. So I typically have to look through code and find a CRC and figure out what CRC reviews are. So I'm only looking at one particular feature. And it's
content page.